Hello everyone, welcome to the second lecture on number theory. In this lecture, I am going to discuss divisibility, some divisibility results, and the famous division algorithm theorem. Let's start with the definition of divisibility. Let a and b be two integers with a not equal to 0. We say that a divides b or b is a multiple of a if there exists an integer q such that b is equal to a times q, where a is called divisor of b. In this case, we write a divides b. The line between a and b indicates that a divides b. If a does not divide b, in this case we write a does not divide b. Let me ask a question. 2 divides 10? The answer is yes, because there exists an integer that is 5 such that 10 is equal to 2 times 5. Here 5 also divides 10 because there exists an integer 2 such that 10 is equal to 5 times 2. For simplicity, throughout we will write AB instead of A cross B. Let me ask another question. 2 divides 5? The answer is no, because 5 is equal to 2 times 2.5 and 2.5 is not an integer. Therefore, 2 does not divide 5. I hope you guys understand the concept of divisibility. Now let's prove some results that are related to divisibility. Let a, b and c be integers. The first result states that if a divides b, then a divides kb for any integer k. In this result, a divides b is given and we have to prove that a divides kb for any integer k. I will start the proof by assuming a divides b. If a divides b, then by definition there exists an integer q such that b is equal to a q. I name the equation by equation 1. By multiplying k both sides of equation 1, we get the equation that is kb is equal to kaq. K into aq is equal to ka into q because integers are associative. Ka into q is equal to ak into q because integers are commutative. Ak into q is equal to a into kq, again integers are associative. By applying commutative and associative property, we can write kb is equal to a into kq. Here k is an integer, q is an integer, so kq is also an integer because integer satisfies closure property with respect to multiplications. Put kq is equal to q1, so kb is equal to a times q1. Now there exists an integer that is q1 such that kb is equal to a times q1. Therefore a divides kb, which is the required proof. Here we use the definition that is, if a divides b implies a is equal to bq for some integer q, and if b is equal to aq for some integer q implies a divides b. The second divisibility result states that if a divides b and b divides a, then a is equal to plus minus b. To prove the result, assume that a divides b and b divides a. Then by definition there exists an integers q1 and q2 such that b is equal to a times q1 and a is equal to b times q2. By putting the value of b given in equation 2 in equation 3, we get equation 4 that is equal to a times q1 q2. Since q1 and q2 given in equation 4 are integers, therefore there are possibilities either q1 equal to q2 equal to 1 or q1 equal to q2 equal to minus 1. For instance, if a is equal to 2, then there are two possibilities: 2 equal to 2 into 1 1 or 2 equal to 2 into minus 1 minus 1. There is no other possibility because here q1 and q2 should be the multiplicative inverse of each other, and 1 and minus 1 are the only integers that are self-multiplicative inverse, so their multiplicative inverse exists in the set of integers. No other integers has multiplicative inverse in the set of integers. So a is equal to plus minus b. Hence the required result is true. The third divisibility result states that if a divides b and b divides c, then a divides c. First we will assume that if a divides b and b divides c, then we will prove that a divides c. For the proof, assume that if a divides b and b divides c, then by definition there exist integers q1 and q2 such that b is equal to a q1 and c is equal to b q2. By putting equation 2 in equation 3, we get equation 4, that is c is equal to q1 q2. Since q1 and q2 are both integers, so q1 times q2 is also an integer. Put q1 q2 equal to q3, so c is equal to a times q3. Since there exists an integer that is q3 such that c is equal to a times q3, so a divides c, which is the required proof. Third divisibility result state that if a divides b and a divides c, then a divides sb plus tc for any integer s and t. First we will assume that a divides b and a divides c, then we will prove that a divides sb plus tc for any integer s and t. We have already proved in the first result that if a divides b, then a divides sb for any integer s, and if a divides c, then a divides tc for any integer t. In this result we will prove that a divides their summation as well. If a divides b and a divides c, then by definition there exist integers q1 and q2 such that b equal to a q1 and c equal to a q2. By multiplying s both sides of equation 1, we get equation 3, that is sb equal to a s q1. By multiplying t both sides of equation 2, we get equation 4, that is tc equal to a t q2. By adding equation 3 and equation 4, we get equation 5, that is sb plus tc equal to a times sq1 plus a times tq2. Since the integers satisfy the distributive property of multiplication over addition, therefore sb plus tc equal to a times sq1 plus tq2. In the equation 6, sq1, t and q2 are integers, so the output of their additions and multiplication is an integer. So a divides sb plus tc, which is the required proof. The fifth divisibility result states that a divides b if and only if ka divides kb or any non-zero integer k. We have to prove this result from both sides due to if and only if condition. First we will assume that a divides b, then we will prove that ka divides kb. Again we will assume that ka divides kb and we will prove that a divides b. Assume that a divides b. Then by definition there exists an integer q such that b equal to aq. Multiply k both sides of equation 1. We get equation 3. By applying associative property, we get equation 4. Since in equation 4 kb equal to ka times q, therefore ka divides kb, which is the required proof. Conversely, assume that ka divides kb, then by definition there exists an integer q such that kb equal to ka times q. Multiply 1 over k both sides of equation 5, we get equation that is b equal to a times q. So a divides b, which is the required proof. Let us prove the division algorithm theorem. The division algorithm theorem states that let a and b be two integers with a positive, then there exist unique integers q and r such that b equal to qa plus r, where r greater or equal to 0 and less than a. To prove the theorem, assume that let a and b be two integers with a positive. Since the floor of b over a less or equal to b over a, let us discuss the floor function first. For a real number x, the floor of x is the greatest integer that is less or equal to x. For example, the floor of 3.333 is 3, because 3 is the greatest integer that is less than 3.333. Similarly, the floor of 4.999 is equal to 4, because 4 is the greatest integer that is less than 4.999. the floor of 5 is equal to 5 because 5 is an integer. 5 is the greatest integer, that is equal to 5. From the examples, it can be seen that if x is a decimal number, then the floor of x is less than x. However, if x is an integer, then the floor of x is equal to x. So in this case, if b over a is an integer number, then the floor of b over a will be equal to b over a. If b over a is a decimal number, then the floor of b over a will be less than b over a. For instance, if b is equal to 10 and a is equal to 3, here 3 does not divide 10, implies 10 over 3 is not an integer number. 10 over 3 is a decimal number, that is equal to 3.333, and the floor of 10 over 3 is equal to 3. So the floor of 10 over 3 is less than 10 over 3. Now for b is equal to 15 and a is equal to 3, here 3 divides 15, implies 15 over 3 is an integer number, that is 5. And the floor of 5 over 3 is also equal to 5. So in this case, the floor of b over a is equal to b over a. Therefore, we write the floor of b over a less or equal to b over a. Put q equal to the floor of b over a. So q less or equal to b over a less than q plus 1. Q less or equal to b over a, multiply both sides by a. A and 1 over a cancel each other, we get the equation that is aq less or equal to b. Subtract aq from both sides, we get the equation minus aq plus aq less or equal to b minus aq. Minus aq and plus aq cancel each other, we get the equation that is 0 less or equal to b minus aq. Put r is equal to b minus aq. So r equal to b minus aq. Add aq to both sides, we get the equation aq plus r equal to b minus aq plus aq. Minus aq plus aq cancel each other, we get the equation b equal to aq plus r, which is the required proof. To prove the second part of the theorem, that is r greater or equal to 0 and less than a. Since 0 less or equal to b minus aq and b minus aq equal to r, so 0 less or equal to r. We have to show that r less than a. We will show this by contradiction. Assume that r greater than a and r equal to b minus aq, so implies that b minus aq greater than a. By adding aq to both sides of the equation, we get the equation that is b greater than aq plus a. Now by applying distributive property of multiplication over addition, we get the equation that is b greater than a into q plus 1. Now divide both sides by a. We get the equation that is b over a greater than q plus 1. But b over a less than q plus a given in the equation star. The fact given in the equation star is contradicted because of our wrong assumption, that is r greater than a. So r less than a, which is the required proof, where q is called quotient and r is called remainder. The question is how to compute quotient and remainder. In question 1, the values of a and b are given, where a is equal to 9 and b is equal to 33. We have to compute the quotient and remainder for given integers a and b. Since we know from the proof of division algorithm theorem that q equal to floor of b over a and r equal to b minus aq. So q equal to floor of 33 over 9, which is equal to floor of 3.666, which is equal to 3. So q equal to 3. So the quotient is 3. To compute the remainder, since r equal to 33 minus 9 into 3. So r equal to 33 minus 27, which is equal to 6. So the remainder r is equal to 6. We can write 33 equal to 9 into 3 plus 6, where 33 is the value of b, 9 is the value of a, 3 is the quotient, and the remainder r is 6.